Hey Opties! Today we're talking about inverses. We're going to look at inverses in three different types of ways. That will be algebraic, graphical, and tabular. So let's take a look at algebraic first. First of all, an inverse function is a function that undoes the action of the other function. So just think about when we talk about inverse operations, if we're solving an equation, to undo addition, you'll subtract. To undo multiplication, you'll divide. So this is like undoing an entire function if we're finding an inverse function. That's what happens algebraically. So let's take a look at an example. This example has two given equations where we know they're inverses of each other. That's y is 2x plus 6 and y is 1/2 x minus 3. So we're going to look and see what happens when you substitute one of the functions into the other. So putting an entire function in for x into both equations. So we have the first equation, y equals 2x plus 6, but instead of writing x, we wrote the entire equation, or the entire function, 1/2 x minus 3. Now if we distribute this 2, then we have 2 times 1/2 is 1, so that'd be 1x, so that's how we got this x here. And then 2 times -3 is a -6, and then we had the plus 6 on the end. X minus 6 plus 6 is x plus 0, which is just x. So we're left with only an x. Let's look at it the other way. Put 2x plus 6 as a substitution for x into the equation, y equals 1/2 x minus 3. We distribute our 1/2. 1/2 times 2 is 1, so 1x. 6 times 1/2 is positive 3. And then you have the -3, so x plus 3 minus 3, and that's x. So notice it undoes all the extra stuff and always goes back to x. So here's how we know that they're inverses if we want to verify that algebraically. It says here the functions undo each other by resulting in just the x variable upon substitution. That's the rule for checking if two functions are indeed inverses. But here are the steps to take if you actually want to start with a given function, given function's equation, and figure out what the inverse is. So in this case, you're not given two inverse functions, you want to find an inverse function given just one function. So step 1, if the equation is written in function notation such as f of x, rewrite f of x as y. Step 2 is to swap x and y, so swap the position. Instead of writing y, you're going to write x. Instead of writing x, you're going to write y. Step 3 is to solve your new equation that you just got from swapping x and y for y. And step 4 is to rewrite your y as f of inverse x. So that looks like a -1 right here. So f inverse of x is like a -1 that looks like an exponent. It's not an exponent, but it's up as a superscript like that. So let's look at this example. We're going to start with f of x is 2x plus 6 and see how we get the inverse way down here that we were shown in the beginning. So we're going to write f of x as y, and then we swap x and y. This y becomes an x, and this x becomes a y. Then we're going to solve this equation for y. Subtract 6 from both sides, and those become a 0. And then you have x minus 6 equals 2y. Continuing, you divide both sides by 2. That becomes a 1. And then x over 2 is 1/2, so 1/2 x. -6 divided by 2 is a -3, and then you're left with y. You can rewrite that with y on the left if you so choose, and y equals 1/2 x minus 3. To show that it's truly an inverse, we put the f of inverse x notation instead of our y. So here's our final inverse. And we saw earlier that this y equals 1/2 x minus 3 was up here as our inverse. So that's how we do algebraic inverses. Let's take a look at graphical representation of inverses. Function inverses are represented graphically by being reflections of each other over the line y equals x. So the y equals x line is dotted just so you can tell where the reflection line is. So we've got two functions here on our first graph. They're lines, so they're both linear functions. And you can see that they reflect over this dotted line, which is the y equals x line. So here's what it would look like when you have two inverse functions graphed on the same graph if they're linear. Just one example. If we see here, we've got a Superman curve, so our cubic, and then we've got a sideways Superman, so a cubed root. Those are inverses of each other, and you can see they're reflections of each other, and I think this makes it look really pretty. Thirdly, we have, this is an exponential function. We'll learn about that more later in a different unit. And this is a logarithmic function. We'll learn more about that later as well. And they're inverses of each other. You can see that they're reflections of each other over that line, y equals x. Notice that it says y equals x. Well, isn't that the same as x equals y? You can swap the order, right? That's exactly what we did algebraically. So you can see how the algebraic method and the graphical method go together that way. You're still swapping x and y. Now let's take a look at a tabular method to view inverses. Just like algebraically and graphically, finding an inverse, x and y are being swapped. So x and y are being swapped in any of the methods. That's a really key idea for function inverses. In two tables of inverses, the points are the same numbers with x and y of each coordinate swapped. So in a table, it's really easy to tell what are your inverses because you've literally just swapped the position of x and y. We already know these two functions are inverses of each other. We verified it with substitution and we did it with algebra. And that was our original example over here for the algebra. Notice for x on this first table, it's 0, 1, 2. And now 0, 1, 2 have become the y values. On this first table, the y values are 6, 8, and 10. And now they've become the x values in the second table, 6, 8, 10. So you're literally swapping the position of x and y in all three of them. It just looks a little bit different for each of them.